I hope that you guys are having a great start to your day. We've got just a handful more meetings. And then yowza. Oh, it's chilly? Oh yeah, definitely. Um,
At her concerts for the past few days. I feel like it should be very well known by now that Sabrina Carpenter is not the most PG singer in the entire world. And
okay. I think I forgot to say, or I forgot to set it up to mute everyone upon entry. I learned a little bit about Sabrina Carpenter. I know who that is. I've heard of that person, but that's about it. I've heard of her. She's a musician.
Yeah.
Yep. Um, at any rate, we've got
Right here. Sorry. It's all right. Thank you.
I'm sorry. Sorry, I muted you. You can unmute yourself, Corazon, if you need to. Okay. It is Friday the 22nd. We are going to talk a little bit more about strong acids and strong bases. We got a couple of questions. Um, and I had some questions about Top Hat questions, or I've had some emails about Top Hat. And one thing that I want to say is like the reason that I'm doing Top Hat and the reason that I like to use Top Hat is because what I'm looking for is kind of a sense of during class is what I'm explaining to does it make sense? So I know that you guys are probably interested and curious and actively interested about, oh, well, did I get those top hat questions? Um, or did I get those top hat points? Or oh, if I get this one right or if I get this one wrong, how's that going to impact my grade? I just want to lead with if you get a question right or wrong, I'm not going to like, I don't want you to lose any sleep over that. I don't want you to think like, oh man, I was going to make an A, but I got a B because I got two top hat questions wrong. Um, I'm using Top Hat largely as, or I'm using Top Hat as how are people responding? Do you get this? Do you understand this? Um, and that's like, is it going to be worth my time to explain something in class or does everyone have it? So that's what I'm looking for. And then I also assign it as a homework, or not necessarily homework, but I also set it up for those of you who watch the class after, and then you can do those top hat questions alongside those so that I can see that you've engaged with the class. So I want engagement. I want you to try something. I want you to think about it before you try it. I don't want like, oh, well, I don't care. I want you to be like, I think it's A. Am I going to be wrong? Maybe. But my best guess is that it's A. Okay. Um, and in the event that closer to the end of the semester you have questions about your top hat grade or anything like that, let's talk about it. But for the time being, that's what I wanted to mention. Um, and I know that there is one person in this class who sent me an email like a week and a half ago, maybe even longer than that. And I still have not resolved the issue with them. I apologize sincerely to that person. And I think that person sitting in here probably knows exactly who I am talking about, but I'm not going to identify them by name. Okay. So strong and weak acids and bases. We talked about these a little bit. And I always think that whenever we're talking about strong acids and bases, I think that it's good to come up with analogies. I like to think of analogies because it helps me understand things. It helps me process information, rather than just the like, no, this is what you need to remember because this is what it is. That's tough for me sometimes. So strong and weak acids and bases. Now we've talked about a couple of these, and HCl is a strong acid. NaOH is a strong base. Vitamin C is a weak acid. Vinegar is a weak acid. NH3 or ammonia, that is also a weak base. Now, we talked about specifically, oh, wait just a second. Um, that's not the one that I wanted to do. We talked about those different acids and bases, and we looked at a couple of different models for acids and bases. I'm in the right folder. Sorry, just one second. Um, and when we talked about acids and bases, what we were really kind of focusing on is basically the the percentage that the different atoms in an acid or a base separate from one another. And in that realm, let me see if this is a question that I want. Okay, yeah, this is the one that I want. So I wanted to jump into a top hat question about acids and bases. Now, I wanted to jump into a top hat question about a strong acid. And then we're going to come back and talk about a titration in just a moment. But here what we have is sulfuric acid. Sulfuric acid is a strong acid and has a formula, and its formula is this right here, H2SO4. Now, before you answer this question, before I show the top hat question, could somebody add to the chat what the overall charge of H2SO4 is? Close. H2SO4. And I'm sorry, this right here, this dash is really just kind of a hyphen. It's like, hey, here's the formula, and now let's move on. Caitlin, that's absolutely right. SO4 does have a -2 charge. So if you're just talking about SO4, that is 2 minus. So now with that information, what is the overall charge? Neutral. Absolutely right. Let me block this out right here. So H2SO4, that is basically 2 hydrogen ions and 1 SO4. So 2 positives and that SO4 with the 2 minus, 0 overall. Okay, now keeping that in mind, if you get solid H2SO4 and throw it into water, well, it's going to make a strong acid solution. My question for you is, what's going to be in the water? We've got H plus, SO4 2 minus. We've got H plus, and then SO4 1, HSO4 1 minus. We've got H plus, HSO4 1 minus, and H2SO4. Now, when you think about this and when you're answering your question, keep that little piece of information in mind. I'm going to bump it up about, give you 15 more seconds on this one. Okay. Okay, it's almost done. We're wrapping up. And what do we have? Okay, so as a strong acid, strong acids completely dissociate. They completely separate. Now, this is a particularly challenging question because you've got 2 protons and SO4. Let's look at the spread of the answers. Okay, the majority of you got this answer correct. And then, the answer that came, basically the second place answer, I like that you guys answered this. So I'd rank this as first, second, and third. Okay, and then this would be fourth. Now, the reason that this one is correct is because it is a strong acid and will completely, the protons, these H pluses, will completely separate from the SO4. Now, if there were 3 hydrogen ions, all 3 of those hydrogen ions would completely separate from the negatively charged thing. Okay, now I like this one as kind of a second place answer because it's got elements of being correct. And the reason that I say that is because there are some compounds, or actually, let me rephrase that. Um, this is a good answer because it is kind of a stepwise thing. So if you think about H2SO4, oh, that's a three. I know that's a three, everyone. Um, H2SO4. Well, it's a process. This H2SO4 will lose one proton at a time. And for it to lose one proton at a time, it will look something like this. H plus plus HSO4 minus. Okay. So H2SO4 loses the first proton. Now, the second proton, well, that will also be lost. And it'll end up looking like this. H plus plus SO4 2 minus. So then when we kind of scribble out the HSO4, because that's kind of common, all of the products of the ionization of H2SO4 are these right here. So I like this second place answer as a good alternative because you are understanding like, hey, it's got to lose the first one before it loses the second one. Will it lose the second one? And in this case, yes, it will. There are some instances where something won't lose the second or the third or fourth or whatever, but this is an instance where sulfuric acid is a strong acid and it will lose both of those protons. So what's going to end up in the solution is this right here. So I really like what you guys said with your answers. Majority got the answer correct, and then the majority of the majority of people who did not get the answer correct, they picked that second best answer. So I like that. Great job, everyone. Now, let's proceed from here. So we're still talking about strong acids and strong bases. Now, whenever we're talking about defining a strong acid or a strong base, it's all about how much it will dissociate. It doesn't necessarily mean, well, will it destroy, aluminum? Will it destroy titanium? Is it toxic in this sense? That definition is not, or the definition for acid or base strength doesn't really relate to how much something will destroy. Think about it kind of exclusively as, well, how much will it dissociate? Now, there is a very important technique in chemistry, and this is like classical chemistry. This is a sort of technique that's been done for, I would venture to say, 200 plus years. I would bet, yeah, I would bet that a titration's been done for 200 some odd years. Now, this technique allows you to determine how much of something else is in there. So this is typically done. This is typically referred to as an acid-base titration. So you have an acid, you have a base. And what you're going to do is if you look at the top here, there we go. This right here is a little valve. That's a valve, and it's Teflon, or it's some sort of plastic, basically, that has a really small hole. Can everyone say in the chat if you can see that super small hole in that piece of plastic? Or better yet, I think. Can I zoom in? No, that's not working. That wasn't working like I wanted. And now I'm zoomed in some weird way. Okay, but there's where that point of my arrow is going to, there's a very, very small hole. And when this valve right here gets rotated, well, then that hole opens up and allows the solution from here to flow through and drip into this beaker at the bottom. So this piece of instrumentation is known as, and I always love to mention this just because it's an easy name to misspell. It's a burette. It's an easy one to misspell because lots of times people will be like, oh yeah, like the hat they wear in France. The hat they wear in France, and I'm not sure, I've never been to France, so I don't know how common it is. I'm guessing it's probably not everyone. I'm guessing it's probably like people from outside of Texas are like, oh, you live in Texas? How many horses do you have? Oh, really? You have a car? Huh. At any rate, I'm guessing not everyone in France wears a beret, but a beret is the hat, a burette is the instrument that's used in chemistry. And that burette is filled with the base. The beaker down below is filled with an acid. And then there's this solution right here, which is what is known as an indicator solution. And that indicator solution is sensitive to pH changes. And with that solution being sensitive to pH changes, what that means is it will change color based on a pH change. So initially, this indicator solution, and the most common indicator solution, is a solution known as phenolphthalein. And it's got phenol, PHTHALEIN. Phenolphthalein. Okay. Phenolphthalein is a solution that's commonly used in acid-base titrations. And the value of a titration is it allows you to say you have a known concentration of a base and you add that to an acidic solution, and that allows you to determine the concentration of acid. Now, an acid-base titration is just one example of a titration. Titrations are used in many other instances as well. Titrations, you could think about them as basically a technique to determine the concentration of a substance. Now, to give you a little bit more information, titrations are done not just in chemistry labs, but they have lots of clinical significance in clinical applications. So in many cases, well, if you, what might be done is drug tests where, maybe there's some or some sort of compound in a bloodstream or something like that. Well, you'd do a titration and you'd say, I know that there's this much of substance A here, your known concentration. Whenever I add it to this blood solution, does it change color? If it does, then I have a sense of, or I can kind of extrapolate or calculate the amount of that substance that's in my concentrated solution. So that's just one other example. Now I'm going to erase that because I want to focus on an acid-base titration. Now, with an acid-base titration, we've got sodium hydroxide up here. We've got HCl right here. Now, that sodium hydroxide has a basic pH. So the pH here, give me a number that would be a basic pH. Or a number that would be a representative of a basic pH. 10. Perfect. I love it. pH of 10. Okay. And now our HCl, or our acidic solution, has an acidic pH. So for that, we're probably looking at, let's call it 4.0. So we got 10.0 up here, 4.0 down below. Now, phenolphthalein, as our indicator solution, it is going to turn to kind of a very, very faint pink solution whenever it has a more basic pH. And what you're looking for is, and if you look at this right here, um, it might be a stretch for you to look at it and be like, yeah, that's a pink solution. I mean, I always kind of look at that and I'm like, it looks like a clear solution that's held up to a pink piece of paper from a long distance. And that's kind of what it is. And we are looking for this pink solution to emerge whenever we've added enough sodium hydroxide to neutralize our HCl. So this is basically pink when it's basic or neutral. So I want to show you guys what exactly a titration looks like in practice. The tab open up. Okay, I gotta clear all my drawings. So here is a titration. And blow this up. There we go. And this person's hand on this valve up here, and then they've got their hand on, and where their hand is on the valve on the burette, that's where your basic solution is going to flow from. And then the beaker or the Erlenmeyer flask down below is where the acid is going to be. So I can write on here, I could say we've got HCl. No, that's not what I wanted. HCl down here, and then NaOH up here. What is also in this is our indicator. And that indicator is going to tell us whenever we've reached a neutral pH, the solution changes color. Okay, so I'm going to press play. That indicator is there. Okay, now it's tough to see because the person's hand is blocking it, but look at the valve right up here. And I'm going to scrub back a little bit to show you how that valve changed. Okay, so there it is in that position. That would be considered the closed position. Then we're going to adjust it. And now it's in the open position. So the solution, the NaOH solution, can flow through the burette into the acid plus the indicator. You're going to swirl it around to get it to mix. And if you watch it slowly and watch it very closely, you might be able to see that the color is changing ever so slowly and faintly. Continue on, continue. And oh, there we go. We're seeing a little bit of the cloudiness of the color change. Okay. There we go. I paused it, and that's where you can see that indicator solution is becoming more abundant, more present. And then you keep swirling. And as you swirl, the solution disappears, which just kind of shows that you haven't completely neutralized it. Swirl. And where are we? We're getting there. There we go. Now, that is basically the end point of a titration. Now I'm going to go back to show you the solution at the very beginning. There we go. There we go. The pigment of the solution has definitely changed, which shows that we have totally neutralized that base. Now, that technique, what I want you to know about a titration, here are the things that I want you to know about a titration. I want you to know the parts in solutions and where those solutions are. So what I want you to know is you use a burette. And just to kind of speed things up, in that burette, that's where you add NaOH. In addition to that, you're going to use an indicator solution. And what that indicator solution is going to do is it's going to change color based on the pH. Now, we've used a specific indicator, phenolphthalein, PHTHALEIN. Crazy spelling. That's the only word I can think of that has PH followed by TH in it. Phenolphthalein. And that is, I'm going to say pink when, say light pink when neutral slash slightly basic. Number 4, you use a Erlenmeyer flask. And in that Erlenmeyer flask, that's the beaker at the bottom, the flask at the bottom, that's where you're going to add your HCl. Those points right there, there's absolutely going to be a test question related to those. Okay, so expect that. And if you know those, you're in good shape. If you want to like take a screenshot or, take a picture of that right there, great idea. But those items right there are going to be, in fact, I'm going to take a picture of this. Done. So I've got it. One of those things is going to be asked on an exam now, or on both the exam number 4 and the final exam. Now, to follow that up, we've already answered this question, so we're going to move past that. Now we're going over here to look at a neutralization reaction. Okay. So here what we have are the different reagents of a neutralization reaction. And here what we have are our lists of strong acids and bases. Um, these are strong acids and strong bases. And it's very common that you're going to use a strong acid and a strong base in a titration. So these strong bases, those are what are going to be found in your burette in a titration reaction. Now, what I want you guys to be able to do is to look at and know these strong acids. I want you to remember these names of your strong acids and of your strong bases. Now, what took me a long time to understand in my classes was that these are basically the only strong acids and the only strong bases. Now, are there some bases that are stronger than other bases? Yeah, there are. But if it is not listed on this table or on this table right here, it is a weak base. So now we can think about that in terms of the top hat question we asked earlier. If you were to make a solution of SrOH2, if you were to get solid, this is strontium hydroxide, what is going to end up in that solution? So you get solid strontium hydroxide and you add water to it. What's going to be in your solution? I'll give you a second to add, and I want to see answers added to the chat and all of the answers, or all of the components added to the chat. And I'll give you one to, or actually, no, I'm going to let you guys try to answer this one. So SrOH2 is a strong base. So what does a strong base do in water? Great questions, Caitlin. So SR it's going to split off and it's going to form SR2 plus. Because remember, this is going to be a strong base. Then a little bit of a hint that you probably either know or you've deduced. OH is hydroxide, and that's going to have a -1 charge. So it's going to appear as OH minus. Now, taking that into account and all of the different kind of markings on there, SrOH2. SR2 plus is absolutely going to be in the water. Kaylin's got it. Yep, 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 yep. 100%. We're going to have SR2 plus, OH minus, and OH minus. Now, as a follow-up question, and feel free to add to the chat, is there going to be any SR, let's say, oh, I'm going to erase that. Is there going to be any, let's go with SROH. And since OH is a negative, let's say SR with 1 OH, so that's going to be overall plus 1. Is that going to be in there at all? Is SR going to pair up with one of those hydroxides? Give you a little bit of a hint. The correct answer starts with an N and ends with an O. Perfect. Absolutely. So SROH with a +1 charge isn't going to be in that solution because this is a strong base. It will split up as SR2 plus and OH minus. Now, if we look at let's go with how about we talked about sulfuric acid, but let's talk about chloric acid, HClO3. HClO3. I think people have a tendency, whenever they see that ClO3, they kind of jump to conclusions. And they say, oh, well, that's going to split up into ClO and O2. Nope, don't fall into that trap. Anytime you see an acid, think about it as it's 2 parts. And those 2 parts are going to split up. One part is a hydrogen ion. The other part is basically everything else with a negative charge to offset that hydrogen ion. So HCl3 is going to split into H plus and ClO3 minus. So that's how we're going to divide that up. Okay. Now, it's a strong acid, so if we added HClO3 to water, we're going to have nothing but hydrogen ions and ClO3. There is going to be no more of this left over because it's a strong acid. Now, let's say that I'm going to erase all of this, and we're going to play around with some answers or play around with some questions. Let's say that we reacted HClO3 and SrOH2. We have an acid and a base. When you add an acid and a base to one another, that's known as a neutralization reaction. So an acid-base neutralization is kind of the common terminology that's used. Now, in order to kind of figure out how these 2 things are going to mix up, what I think is really helpful is to take that acid, say, what does that acid split up to? It splits up to H plus and ClO3 minus. Okay. What does that base split up to? That base is going to split up to SR2 plus, and here's where I'm going to put plus 2 OH minus. Okay, so these are all my reactants. Now, what I'm going to do is I'm going to say plus, add that plus there between them, because I'm adding all of these different components together. Now, essentially, what that means is I've got some floating around in my solution. I've got some of these. There we go. I got 2 of those. I got 1 of those, or a ratio of 1. Yeah, I got 1 of those, and then I got 1 of these. Okay. Now, whenever these ions in solution are going to pair up with something, what are they looking for? Are they looking for something with the same charge or the opposite charge, or a charge opposite to them? Absolutely, Caitlin. They're looking for something the opposite. So H plus, in that solution, it's going to see ClO3 minus, and it's going to be like, oh, cool, yeah, but we don't really pair up together. So I'm not going to pair up with you. What's H plus going to pair up with? I feel like Caitlin's ready to answer this one. And if you're not, don't feel pressure. Perfect. Perfect. Because H plus, a positive ion, it's going to see Sr2 plus and be like, no, I'm not interested. But it will also see Sr2 plus, and it will also see OH. It's going to say, okay, cool, great. Now, what OH is going to do with H plus, is it's going to form H2O. So we're going to form that H2O. Now, you might be looking at this coefficient, that 2 out in front, and being like, ooh, I got to figure this out. You do, but not right now. Okay? So then that leaves behind, and I'm going to go ahead and cross this out to say, yeah, we've dealt with the H plus and we've dealt with the OH. What else do we have? We got ClO3 minus, which is negatively charged. Then we got Sr2 plus. They're opposite charges. So do they seem like they could pair up with one another? Yeah. Now, how would we write an appropriate pairing of Sr2 plus and ClO3 minus? I'm going to start it out, and I'm going to say Sr. Now, I'm going to write ClO3. If those two things came together, what would the charge on those two things be overall? Well, if 2 plus, Sr is 2 plus and ClO3 is minus 1, if those two things came together, it would be, well, it would be plus 1. Now, anytime we form a compound, what do we want the charge of a compound to be? We want it to be neutral. So how could we get ClO3 and Sr2 plus to make a neutral compound? And you've got a little bit of flexibility with this. And you could use this as kind of a model. I can give you a second to add that in to the chat. We'd have Sr, then a parentheses, ClO3, close parentheses, 2. And that would give us our neutral compound. So we've now accounted for the Sr, and we accounted for the ClO3 minus. What we still have to figure out is the numbers. We still have to balance it. But the important part about this is we've figured out the ratios of the compounds that are going to be output. We've got Sr, ClO3, 2, and then H2O. Now, we can classify these different compounds. We've got HClO3 that's classified as an acid, SrOH2, which is our base, water, which is classified as our water, and then SrClO3 is classified as something known as salt. Now, it is not NaCl, it is not table salt, but that is an example of a salt. Okay. Now, what we need to do is I'm going to write these substances up here. And then I'm going to do some erasing. And then we're going to balance this. So my erasing begins right now. I'm going to leave water and salt down there. Okay. Now, with this in mind, let's take into consideration and count up all of the different species that we have on the left and right-hand side of the reaction. How many ClO3s do we have on the left-hand side or the reactant side of our reaction? Got one. How many do we have on the product side? How many ClO3s do we have on the product side? 2. Okay. Those aren't balanced. So how do we balance that? Anyone have an idea on how to balance to get the number of ClO3s on the reactant side equal to the ClO3s on the product side? I'm going to give you a little bit of a hint on the screen. Oh, dang it, Caitlin. You're absolutely right. Stole my opportunity to give the hint, but you're absolutely right. We put a 2. No, don't apologize for that. Perfect. Thank you very much. So we put a 2 in front of the HClO3. Okay, so now we can go ahead and change this. 2. We're balanced there. Okay, now what I like to do is I'll look at my Sr, strontium. We've got 1 on the reactant side and 1 on the product side. So we're good there. Then, let's see, what's left to balance? I'm going to do some erasing, and then I'm going to do some adding. Okay, so, and you can look at this almost like number of atoms. How many hydrogens do I have here? 2. I've got 2 OHs. How many hydrogens do I have there? Just counting the hydrogens, I've got 2 hydrogens and then 2 oxygens. Now, when it comes to adding up and totaling the number of carbons and hydrogens, just look over at water. Well, that's a 2-to-1 ratio. We've got a total of 4 hydrogens over here. Now, do we need to put a coefficient in front of SrOH2? Nope. Do we need to put a coefficient in front of SrClO3 too? Nope. The only place that we need to put a coefficient is we need to put a 2 in front of the H2O, because that's going to get us to the point where we have a completely balanced chemical reaction. So I'm going to erase that, and we're good. Okay. Now this is a great example of a neutralization reaction. Acid plus a base produces salt, which is our general class of a compound, and water. I want you to kind of commit that to memory. And then I want you to be able to look at, and we'll do this as our last activity of the day. Look at sorry, the reactants of a neutralization reaction. We can start at the top. What does H plus OH produce? That produces water, or H2O. Okay. Now, these next two are a little bit tricky. HCl and CaOH2. What do we know? We know that H plus and OH, they love to pair up. And they love to make, and I always like to put my water second, H2O. Because then I kind of don't have to worry about it for a minute. Because I know that water and a salt will always be produced in a neutralization reaction. Now, what's left over then? Well, what's left over if done and done? And again, I'm not worried about my numbers, my coefficients. I'm looking at the individual kind of species. Okay. I'm going to make something with Ca and Cl. Now, my question for you guys is the compound that I'm making, is the salt that I'm making, is it CaCl? Or is there another detail that I need to add? And I'll tell you, there is another detail that I need to add, but what is that other detail? Boom, CaCl2. Because I know that this is +2, each hydroxide is -1, and I've got two of them. Hydrogen is +1, and Cl is -1. So I get CaCl2. Now, do I need to balance anything? I do. Well, I've got two chlorines on my product side right here, and I've got one on my reactant side. So I'm going to put a 2 coefficient in front of that. Now that means I have two chlorines on each side. I'm good. And now I've got two hydrogens right here. I've got two more hydrogens right here. And so all that I need to do is put a 2 in front of that. Calcium chloride, does that need any sort of coefficients? It doesn't. Okay, so this is a good example of a neutralization reaction. H2SO4 plus NaOH. Well, I'm going to be making water, so I'm going to put H2O there. Then that's going to account for my hydrogens and my hydroxides. I like to just kind of scribble those out before I really worry about balancing them. And I'm going to be left with Na and then SO4. Now my question is, do I need any subscripts or anything like that? I do, because SO4 is -2. And I can deduce that from this H2SO4. Or I could just kind of have that in my memory or see it on the polyatomic ions. Na is +1. So I've got Na2SO4. Now to finalize this, what do I need to balance it? Okay, I've got 2, then that would be 3. Oh boy. So that would be, sorry, that's one hydrogen. There's two hydrogens. Okay, I don't really want to work with the hydrogens because they give me a odd number. What about my sodiums? Put a 2 in front of that. Now the sodiums are balanced. Okay, what does that mean for my hydrogens? Now I have 2 over here, so I've got a total of 4. So if I throw that out there, I'm good. I'm balanced. SO4s are good. Sodiums are good. Hydrogens are good. Oxygens are good. And that is my balanced chemical reaction. I want you to be able to balance a neutralization reaction, and I want you to know what the products of a neutralization reactions always is. In addition to that, what we talked about today was we talked about what is in a solution when you get a strong acid or a strong base and you add it to water. How does it break up? Now, I am going to go ahead and tell you that Monday is going to be a pre-recorded lecture, but basically I'm going to have office hours during that time. So if you want to meet, by all means, just send me an email and we can meet, or I'll send out my Zoom link at the typical time. And then if you want to join in, you're welcome to. Other than that, though, I hope you guys have a great weekend. And since Monday's a pre-recorded lecture, then if I don't see you, then I hope you enjoy your break. And that's all that I got for today. Oh yeah, and you have 3 quizzes that are due on Sunday night at 11 p.m. So make sure to do those on Canvas. But thank you guys for coming to class. I hope you have a good one. Bye, everyone.